Good afternoon, NDC. How's everybody doing out there? Welcome. You ever ask yourself what kind of person goes to a talk called plain text? Well, look around the room. Yes, welcome. So this talk it's either plain text or there's no such thing as plain text. But when I put that in conference programs, you get a different crowd. So we went with the plain text one. But welcome. My name's Dylan Beattie. I've been building websites since forever. I've been building distributed systems since the early 2000s. I run Versatile, which is a company I started in January 2020 so I could do lots of traveling. This is the dumbest idea anyone ever had. And finally now, in the last 6 weeks, I actually realized how it was going to work all along. I'm a Microsoft MVP with the Developer Technologies program. I run the London.NET user group. I also once invented a programming language in a bar as a joke that then the internet got it and they implemented the joke, and now I'm the project manager for the joke. And the joke has a reference implementation and a test suite. It is the programming language called Rockstar. So now it's a lot of fun. You can write songs that look like, programs that look like heavy metal songs. But the best thing about it is that since Rockstar kind of went online and went viral, people on LinkedIn have stopped advertising for Rockstar developers. So that is my lasting contribution to the human race. Now, there are two things I want to say up front about this talk. One, there is a bunch of stuff in here that I learned firsthand from talking to people traveling around countries that used to be part of the Soviet Union, Russia and Ukraine and Belarus. And, what is going on over there at the moment is absolutely awful. NDC and me and all the folks I know are on Ukraine's side. They are doing everything they can to support it. If you want to help, if anything in here is like we could be doing more, go and support these people. This is Paracrew. They are a Norwegian humanitarian response agency based in Oslo, which is where NDC originally hails from. There's a bunch of folks I know from NDC who are actually out there in Ukraine at the moment. Some of them are doing stuff like splicing fiber to help keep networks up. Pardon me. Some of them are delivering massive bags of dog food to the zoo in Kharkiv because the bears in the zoo need someone to look after them while all this horrible stuff is going on. So I looked at the talk and I was like, do I want to take any of this stuff out? And I've left it all in. So all the stuff in here about Cyrillic and Russian languages and stuff, because all of it was just about smart people trying to solve real problems. So I hope that's going to come through in the way that it's presented. Now, the other thing about this talk, I've done this a couple of times now, and I did this at NDC Oslo back in December last year, and they put it on YouTube. And people on YouTube have opinions. And it's got quite a few views on there. It's got about 400 or 500 comments by now. And a few of them are people just pointing out I made mistakes. Because, there's a lot of research goes into a talk like this, and I messed a few things up, I got some things wrong. So I'm going to incorporate those into the talk. But also, there are just some YouTube people, like this guy, Braden Best, who goes, there's no such thing as plain text. Of course there's such a thing as plain text. Plain text is plain text in the plain text MIME type, or more generally without special formatting, using only printable 7-bit ASCII characters with a few exceptions, so UTF also counts, to muddy the waters a bit. 850 words later results in a long final destination as chain of events that ultimately results in Arnold Schwarzenegger going back in time to kill your parents, which somehow causes World War III. I guess people really like that meme, all because you chose to put on a foil hat and die on the plain text isn't real, plain text can't hurt you hill. Braden, put the tinfoil hat on but turn it inside out so it keeps the crazy on the inside, my friend. The world will be a better place. So, with the preamble over, let's talk about plain text. Really? Are we really going to talk about text for an hour? Yes, we are. Because we have this thing, we talk about plain text. We're programmers. We have source code, which is a plain text. And we have YAML files, which are plain text. And we have JSON, and we have HTML, and we have configuration files and XML files. And all of these, the software that we build for our customers has special binary formats for, business data and those kind of things. But when it comes to us doing our jobs, we just sling text files around. And, saying to a programmer, hey, what do you think? Do you like text? They're like, guess, I don't know. Does the question really make sense? But it turns out that the things that make computers cool and valuable and interesting and exciting are that we can take an idea, a concept, a word, a piece of media, some music, or, anything, and we can encode that and put it into technology. And the technology can do something with it. It can, maybe it can send it to Australia. Maybe it can put it on disk so we can go and read it again later. Maybe it can sort it for you in alphabetical order, or it can look for discrepancies, it can look for patterns. But then at the other end, we get the information back out, and somebody else can share in that initial value that we had there. Somebody else can share in that idea. Now, we humans, we invented text writing probably about 5,000 years ago in Mesopotamia and what is now Iraq, because we found historical records of clay tablets and things going back about 5,000 years. And we probably discovered electricity about the same time. Like, there are Arabic texts that indicate people understood that the electric fish in the rivers had something in common with the lightning in the sky, so they were clearly onto something there. But things didn't get really interesting till about 150 years ago when someone went, hey, let's take the writing and the text and mash those together and see what we can get. And they invented this. So this, I think, is the first electrical text encoding system that was ever created. It's a thing called a Cook and Wheatstone telegraph system. It's used in England in about the 1830s. And there's a lot of things about this project which kind of seem strangely familiar. So it's created by two people. Cook was a business person. Cook wanted to sell this to the highest bidder, and Cook was adamant that it should be easy to use and it didn't require a manual. Wheatstone was a scientist. If any of you have ever used a thing called a Wheatstone bridge, he's the person who invented that. And he said, no, it's okay that they should have to read the manual. This can be difficult to use, but we should give it away for free to make the world a better place. So we've got the whole commerce versus open source, usability versus read the manual going on in about 1831. But this device was ingenious. The compromise they eventually came up with was you had to read the manual to send messages, but to read a message from a Cook and Wheatstone telegraph, it had these 5 needles across the middle. Now, this was a 5-wire telegraph system. It was installed in West London between Paddington Station and a town called West Drayton, which is near where Heathrow Airport is now. And they had 5 wires running through the countryside, about 22 kilometers long. And to send a message, you would close a circuit. So you're making a circuit, a loop, that is 40 kilometers there and back again. And you would send a current down that, and these needles would move. And one would be the outbound signal, the other one would come back, the 2 needles would move, and you would read off which letter did they point at. And that's how you knew what message was being sent. Now, it couldn't encode the whole alphabet. There's only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's only 20 characters on here, so they had to fudge the spelling a little bit. But anytime you're banging your head against ASCII or Unicode or any of the other things we're going to learn about in the talk, I want you to think we could have ended up with this. We could have ended up with a 5-symbol trinary encoding system where every letter is a series of 5 symbols which can be positive, negative, or neutral. So I think we dodged a little bit of a bullet there. Now, the telegraph system, the same time Cook and Wheatstone built their system, they put in the 5 wires. After a couple of weeks, one of the wires stopped working. And they're like, we need to fix the wire. So I went, no, come on, let's build a 4-wire telegraph system. And then they lost another wire. And they're like, how about a 3-wire telegraph system? But across the other side of the Atlantic, there's a guy called Samuel Morse who was doing what we call leapfrogging, which is where you ignore the next generation of tech and you focus now on delivering the things going to come after it. And he invented the single-wire telegraph system, and he invented an encoding system to go with it. Now, this is not actually the Morse code that Samuel Morse invented. Samuel Morse invented the single-wire telegraph. He invented the first version of this coding system. It came across to Europe as a German engineer called Friedrich Gerke actually standardized it, and that's the one that some of you are probably still familiar with today, International Morse code. Now, Morse code looks like a binary encoding system. You look at it at a glance, you're like, dots and dashes, that's fine. But actually, there's more to it than that. Because Morse code has dots and dashes, and it's got short gaps, medium gaps, and long gaps. And so it's actually a time-based encoding system. And Morse code was established, it was agreed as a standard in 1865. There was an international telecoms conference in Paris, and all the countries in Europe that were getting telegraph networks were like, yeah, we're going to use this. This is the standard we're going to agree on. Now, as I'm sure you all know, because you work in tech, if nobody is using your system, you can change it whenever you want, because nobody cares. If you have users, you are not allowed to change things, because the users get upset. And so International Morse code was being used by the entire telegraph network, right across Europe, down through Asia, the Middle East, as far out as Australia. Changing it would have been a big deal. And so it lasted almost exactly 100 years. It wasn't until the 1960s that finally the world started going, maybe we need a better system. And the reason was we had invented electrical computers. Now, the system that was developed for this was ASCII, the American Standard Code for Information Interchange. And ASCII was phenomenally successful. When we talk about plain text files today, we are normally talking about something based on ASCII, as we're going to see in the rest of the talk. But the thing you need to understand about ASCII is that it was designed when computers looked like this. And it was designed when they didn't have screens. They had teleprinters, so they would actually physically print out what you were doing. And you didn't store data on disk, or on magnetic tape, or on SSDs. Those hadn't been invented for a long while yet. You stored data on punch cards. So when you look at the design of ASCII now, there's a lot of stuff in it. You look at it and you're like, really? Like, what is all this crap in here? You're like, okay. Now, 0, the null character. Any of you C developers? You've seen null, right? Null survives today. It's the thing in C that marks the end of a string, and if you accidentally go past it, then you can hack into the Pentagon and all kinds of fun stuff. Brilliant piece of design there. Then we have start of heading, end of heading, start of text, end of text. Now, this was all the bottom block of characters here. These are control codes for mechanical teleprinters. It's what they were invented for. They were invented to physically control this piece of machinery with all the clunking moving parts on your desk. And if your teleprinter wanted to send start of heading, you would hold down the control key and you would press A, because A is the first letter of the alphabet, so control A would be that. Control B would be that. If your teleprinter was printing stuff and you're like, no, stop, end the text, you would press Control C. And that has survived today. And, I had to press Control C yesterday because I wrote an infinite loop in some code I was hacking around on. So we have these little relics from the days of teleprinters that still crop up all over the place. End of transmission, inquiry, acknowledgement, yeah, no big deal. Bell, if you've got a Windows machine and you type echo space Control G, and you press enter, it will play tada.wav, because that's how it interprets the I want to physically ring the bell on my teleprinter. Backspace, if your backspace key is broken, you can do backspace by pressing Control H on most terminals, because that's the same control code. And then we get into the tabs, the line feeds, the vertical tab, the form feed, the carriage return. Now, vertical tab is hilarious because it says move the teleprinter vertically until you hit the next metal tab stop. So if anyone ever says tabs versus spaces, tell them you indent your code with vertical tabs and watch as they go and look it up and try and figure it out. But the reason why we had these characters is a mechanical teleprinter used a thing called a carriage. And in order to print text, the carriage would print something. And then you would return the carriage to the start of the line. That's a carriage return. And then you would feed the paper through to the next line. Carriage return, line feed. Made sense. Now, teleprinters were a little bit simple. And if you wanted to do bold, what you had to do was return the carriage, and then you printed the same line again. And it wouldn't overprint exactly, so you could get the pseudo-bold effect. So carriage return on its own was useful. Line feed on its own, not so much. There were very few scenarios where you wanted to move to the next line without getting to the beginning of the next character. Now, this has survived today. If you run devices whose ancestry is based on Unix, so Mac OS, Linux, Android devices, they use a single new line as a line feed. That's the end of a line in a text file. And the reason is that they evolved from Unix, and Unix evolved from a system called Multics. And Multics was the first computer system ever that had device drivers. It's the first thing ever where they had a way of running a little piece of software that sat between your operating system and the physical hardware on your desk. And so they had a place where they could put in this hack to say, if you see a new line, that means also do a carriage return. And translate that character and go to the start of the next line. Windows 11 has evolved from Windows 10, from Windows 8, 7, 5, XP, Vista, 3.1, all the way back to MS-DOS, which evolved from CP/M, which was designed to run on really cheap mini computers that did not have device drivers. And so for those early systems, which are ancestors of Microsoft Windows, you had to send a carriage return and a line feed, otherwise your carriage would fall off the end of your teleprinter. Now, there are some very neat ideas in the next block of ASCII here. One of the decisions that the designers of ASCII had to make is they're like, what punctuation do we actually need? Now, if any of you here has ever worked in print or in typesetting, we have a minus sign, and we have a hyphen, and we have an N dash, and we have an M dash, and these are all different characters if you are printing books and printing scientific papers. The creators of ASCII were like, nah, we don't actually have space for all of these. They kind of look the same anyway. We're just minus sign is a hyphen, is a dash. That can double up on all those. But within the last couple of years, maybe the last decade or so, we've started seeing a resurgence of digital typography because we have retina displays, and we have people reading books on Kindles and iPads, and so we're starting to see things like smart curly quotes and typographers' dashes and these things coming back in. Now, this block here, the decimal digits, one of the most common things that you had to do on a computer was to turn a number into the string that represents that number and back again. And the way you do this in ASCII is you just ignore the top half. You take the bottom 4 bits of that number, and that is the numeric value of the digit that it represents. And this was blisteringly quick. Even on a 4-bit processor, this was really, really quick and easy to do. Now, have you ever looked at ASCII and thought, well, why is uppercase A 65 and lowercase a is 97? Why would they have picked those numbers to represent the beginning of the Latin alphabet? Well, it turns out that those differ by a single bit. So if you want to do a case-insensitive string comparison in ASCII, all you do is you ignore the 6th bit, and then the values of those are the same, and so you can collate based on the numeric value that you have left. Finally, we mop up a little bit more punctuation, and we get to character number 127 right down the end here, and that is delete. 111111. Do you know why that is delete? Imagine you're storing data on a punch card, and you've punched some holes in it that represent your bank records. And now you're like, I need to erase the bank records. Now you could take the card outside and burn it, or you can punch through the rest of the holes so you can't see what the data in the first place was. Now at this point, YouTube steps in and says, delete was never intended for punch cards. And I dug into this, and actually, it turns out they're right. If you deleted a punch card, you ended up with a thing called a lace card, which would fall apart and jam up your mainframe, and everyone would be very unhappy with you. So yeah, pretty pleased with sugar on it. If you're going to talk about computing history, do your research. Thank you, YouTube. They're right, I was wrong. It was actually for these. It was for erasing paper tape. So delete was predominantly used for, and if you look at the left-hand side of the teleprinter there, you can actually see a paper tape punch machine on the left there. So America pats itself on the back. They're like, that's it. 127 characters is all you're ever going to need. And they give themselves, yeah, we fixed the problem of encoding text. And the rest of the world goes, sorry, you did what? Like, we can't use this. You haven't even read any of our alphabet. Now, for some cultures, ASCII was a complete non-starter. I think for most cultures, Chinese, Japanese, Kanji, Korean, Thai, Vietnamese, Arabic, Cyrillic, there are cultures that are thousands of years old all over this planet for whom ASCII was like, all right, you kids have fun, this isn't going to work for us. But for quite a lot of cultures, ASCII was sort of almost good enough. It wasn't there, but it came close. Now, my personal journey with plain text started in 1988. I grew up in Zimbabwe, where I spoke English, and the currency there was dollars and cents. So when I was playing little programs on my dad's Amstrad, it worked. All the characters that I knew about were in the ASCII that ran on the Amstrad 128. But then I moved to the UK, and I did some homework on the computer. It's a 286 PC with an Epson dot matrix printer, and I tried to print this, and it didn't work. And it didn't work because this is not one of the characters that the Americans cared about in 1965, and so it's not part of ASCII. And now what had happened is, after ASCII was published, a lot of people, a lot of companies all over the world, they looked at this and went, well, hang on, ASCII's only 7 bits. Is anyone using this bit? And of course, nobody said, there's an international standard, because there wasn't. And so lots and lots of different people and companies, they jumped in and went, oh, we can use that bit to solve our problem. And this is, if you've ever come across the idea of something called a code page. A code page is a set of rules for saying what the top half of ASCII means on this computer, in this program, in this document, right now, while I'm looking at it. And the reason I couldn't print my homework is that the printer, which was less than a meter away, connected by a cable, was using a different code page to WordPerfect, which is what I was using to do the writing in. Now, one of the most popular code pages, one that has become ubiquitous, was this one. This is code page 437, which was the default code page on the IBM PC. Now, they kept the regular block of ASCII. The top half there they added most of the characters that were necessary for Northern and Western Europe. They added box drawing characters so you could do little menus and GUIs. And then they added half of the Greek alphabet. Do you know why? They took the ones that were used in maths and physics. There's not enough Greek here to write Greek, but there is enough Greek in here to do the most common mathematical and physical formulae, and they didn't have a whole lot of space to work with. They could have put in the whole Greek alphabet, but they went, no, we'll put in the ones that are in the physics textbooks, and the rest you're just kind of going to have to figure out later. But they also said, well, we're not running on mechanical teleprinters anymore. Maybe we could use this top section for little smiley faces and musical symbols and this kind of stuff. And if you've ever seen an IBM PC crash really, really hard, which they used to do quite a lot, you got a screen full of smiley faces and playing cards and nonsense, and that's because the operating system was churning out control codes, which are basically trying to say to the teleprinter, hey, stop what you're doing, and the screen is going, oh yeah, smiley faces, how nice. Now, there was a code page created by ANSI, the American National Standards Institution, for doing Cyrillic, which is the alphabet used to write Russian, Ukrainian, Bulgarian. And it looked like this, but it didn't work very well because of a historical quirk of encoding systems. It was quite common. You would take a word like privyet, which is hey, hello in Russian, and you'd turn this into this set of numbers according to the code page. But quite a lot of systems would ignore the 8th bit. They would strip it off because they're like, oh no, ASCII's only a 7-bit system. Some things used the 8th bit for things. I think WordStar used it to say whether you had spell checked a word so that they didn't have to spell check the whole document. They'd use the 8th bit on a character as a flag for that. Some places used this as archive bit. Some email systems would use the 8th bit as a parity check, so that would get lost in transit. And if you took this and you stripped the 8th bit off and then you tried to turn it back into ASCII using that code page, you got nonsense. And so the Russians went, well, this is clearly not going to work. Let's invent our own system, which is the Kod obnema informacja 8-bit, KOI8. This is IBM code page 878. And this was brilliant, because what they did is they said, right, forget Cyrillic alphabetical order. We are going to take the number or the letters in English which sound kind of the same, and we are going to put those in the appropriate position. So if we get garbled in transit, what comes out the other end is something we can read, which I think is rather neat. Now, there are some wonderful little historical quirks and stories and things. I did this talk at a community event in the UK in October, and someone came up to me afterwards and said, do you know about the Harry Potter book? I was like, what was the Harry Potter book? And they said, so there's this great story, like way back in 2002 or something. There was a lady in France, had a pen friend in Russia, and they were both big Harry Potter fans. They were sending each other email backwards and forwards. And I know from the kind of historical record, the woman was called Svetlana. I've made up Claudette. I don't know who Claudette actually was, other than a woman in France somewhere. And Claudette said to Sveta, do you want me to send you the new Harry Potter book? Because we can get it in France. And Sveta writes back, hey, Claudette, that would be amazing. We can't get the new Harry Potter book in Russia. Here's my address. It's in Russian alphabet. Please copy it carefully. And puts down this, which is a street address in Moscow, and sends that. And of course, Sveta gets this on Windows 98 running in French encoding and goes, okay, well, obviously that's how they write addresses in Russia. Now, this is the same set of numbers. It is the same underlying sequence of bytes, but it's been encoded using a different code page. So what Claudette does is she very carefully copies the email onto an envelope and puts it in the post, and somebody somewhere in the Russian postal system looks at it and goes, I know what this is, and they fill it out. And the book actually arrives there. Now, I'd like all of you now, get your phone out your pocket. If you've got Spotify, Apple Music, Google Play, any of those things, I want you to search for this word on whatever you use to listen to music and stuff. Just take a moment, look that up. What have you found? Billy Joel. Billy Joel live in Leningrad. 1987, Billy Joel became one of the first Western musicians to perform live in the Soviet Union. And they played this big show in Leningrad, and it was released in the Soviet Union, which was very unusual. And it was called Concert. and on the cover of the record, they spelled the word concert in Russian. K-O-N-C-E-R-T. And now at this point, of course, YouTube pops up and goes, yes, Petrograd became Leningrad and later St. Petersburg, and still one is today, as my best knowledge, but it was never spelled Moscow. I'm like, who said Moscow? Nobody said Moscow. And the giant colorful ice creams in the background are actually the Kremlin towers, which are in Moscow. That's actually St. Basil's Cathedral. It is in Moscow, and I never said the photograph was taken in the same place they recorded the album. Come on, YouTube, you're smashing it today. So this album was released as concert, and then it made it across into the US where someone's like, we need to put this into our database. K-O-H-U-E-P-T, okay, I guess. And then streaming is invented, and so Spotify and Apple Music, they go to all the record companies like, do you have like a massive database of all your music? And they're like, yeah, here you go. We made it in WordStar in 1987. You can have this. And now Kohuept is just, that's what the album's called. This weird encoding and transcription error, which is just going to be there forever now. Now, code pages worked as a kind of a temporary solution for a lot of things, but they weren't ideal. They were clever, but you couldn't, for example, you couldn't write a letter which had Hebrew and Arabic in the same script. You couldn't mix different alphabets in the same document. It was quite common that you'd write something you couldn't print, or you'd get something from your printer that you couldn't load on your computer. And as we invented email and the web and everything, it became obvious that code pages was not going to fix this. Now, this is just some of the set of code pages that existed. Windows had about 15 or 20 different ones. Microsoft had some that weren't used with Windows. IBM had their own, IBM had their own alternative to ASCII, which still floats around out there somewhere. Apple had their own ones. There were different ones for PostScript and DOS. The whole thing was a mess. And it was obvious that a unified coding system was needed. And so Unicode was born. The project started in 1988. The Unicode Consortium was established in 1991. And their mission statement, which I think is a brilliant example of a mission statement, was just this: to provide a single consistent way to represent each letter and symbol needed for all human languages across all computers and devices. Now, this kind of breaks down into three things. First of all computers and devices. Now, the way to do that is you've got to build something that is better than any of the alternatives, and you have to make it trivially easy to implement. And they succeeded. You know, Unicode works. Unicode is how people on Danish computers can use Slack with people on Norwegian computers and people on English computers and people on Russian computers, and we can all talk to each other, and it works. You know, it's a brilliant solution, and they did an incredible job of delivering it. But to provide a single consistent way to represent each letter and symbol. Now, all human languages, that was just them going, look, we're going to do ancient hieroglyphics, we're going to do Sumerian, because there's people out there studying historical and dead languages. We don't want to exclude them. So that brings us to a single consistent way to represent each letter and symbol. So what's a letter? You think these are the same? Well, let's start with an easy one. Are they the same shape? Do they represent the same sound? We don't know. It turns out the top one here is horosho, which is Russian, it means good, and the bottom is exoplanet, which is English, and it's a completely different sound, hor and xop. So obviously, we have to agree what a letter actually is. Now, I'm British English. So, good morning, this is London, here is the Queen, would you like some tea? That's the noise playing in my brain all the time. So when I visit somewhere like Denmark, and I see smørpålæg, I'm like, oh, smørpålæg. Well, my brain doesn't know what those mean. Clearly, they can't be important. Let's throw them. And somebody has accidentally mashed together the A and the E. Let me split those out. And so my brain says, this is a smørpålæg. And I'm like, hello, could I have some more smørpålæg, please? Now, this kind of gets us into the question, you know, what is a letter? Are these letters here, are they just the same letters with a little bit of extra decoration, or are they actually completely different letters? Let's meet some friends of mine. So Francois Bordet is an archaeologist from France, and Motley Crue is a rock band from Los Angeles. And this sentence is clearly an English sentence. Francois, the archaeologist, went to the Motley Crue concert. But there are characters in here which are not part of the English alphabet. We got the C with a cedia, and we got this little, the AE, which is a letter in Danish, but it's not a letter in English. And we have the O and the U, which is the heavy metal umlaut. Now, at this point, I want to shout out to Anders, who saw the talk on YouTube with the YouTubes in it, and he said, I want to be in the next version of the talk 2 weeks ago. So, hey, Anders, welcome. We do actually have, any of you read the New Yorker magazine? The New Yorker always spells the word cooperation with an umlaut on it, which is just a weird stylistic thing. So we do get these letters, cropping up from time to time in here. Now, the AE there, in English, that's not a letter. In English, it's something called a ligature, which is a typesetting convention that back in the days when typesetters made books using hot metal printing plates, they would see an A and an E, they go, oh, I'll put in one of the fancy ones for that. And of course, you mention this on YouTube, and you get people going, not a ligature, it's a typesetting detail, la 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 la. And so I did actually go and do a little bit of digging. And here, this is a font that I use, which has ligature support. And they're kind of right. The AE here, that's not really set as a ligature in any fonts anymore. But you can see, if you look at the difference there, the FF on the top, they're joined together. That's a typographic ligature. The TI and the IJ there, these are different ways. But it's the same letters. It's just they're being printed differently. Now, let's meet another friend of mine. Let's meet Magnus. So this is Magnus Mortensen. And Magnus is a Microsoft MVP from Sweden. A couple of years back, he's traveling to the United States, and he's traveling on a Swedish passport, which says his name is Mortensen, because it is. And the rules of Swedish orthography say that if you have O, and you need to put that in the ASCII strip at the bottom of the passport so that American computers from the 1960s can read it, you replace O with AA. So he gets a plane ticket, which is not issued by the Swedish government, and they just take the circle off because they don't know what it means. So he ends up with a plane ticket that doesn't match the name on his passport, trying to get into the United States of America, who are a famously friendly bunch. And he gets into has to answer some questions. Now, Magnus is a well-dressed, affluent European white guy on his way to go and do an event at Microsoft. You can see how for somebody else, that scenario plus United States border control could have worked out really, really badly just because of a disagreement about what a letter is and how they get encoded. And if you think one letter is a bad idea, let's start talking about alphabetical order. So here is a list of European cities, and here is angry people on YouTube saying Zurich has to have an umlaut on it, and here is me saying, very sorry, Internet, yes, I will do Zurich with an umlaut on it. Now, which one of these is in alphabetical order? Raise your hand if you think list number 1 is in alphabetical order. Number 2? Yeah, we got one at the back. Now, actually, I should put mine up. Number 1 here is clearly in alphabetical order, because A comes before B, B comes before O, and O comes before Z. We got a couple of folks at the back for number 2. List number 3. And list number 4. Yeah. Now, how can that be in alphabetical order? I mean, let's look at it slightly differently. How about now? Now who thinks that number 3 is in alphabetical order? Yeah, we got a couple of people change their mind on that. Alphabetical order wouldn't seem like one of those things that you can have a disagreement over, but it turns out you can, because different cultures use different alphabets, as I'm sure many of you in here are very, very well aware. So we're going to take this list of names and we're going to put them into our Microsoft SQL Server database, Berlin, Aachen, Zurich, Aarhus, and Örebro. And we are going to then do a select star from cities. There we go, that's fine. Let's select star from cities where name equals Örebro. Oh. Will we put it there? It was there a second ago. Maybe it's case sensitive. What about Örebro with a big O? And it's like, nope, that's still not there. Well, let's, is Örebro even equal to Örebro? And we're going to run that, and it's going to say no. Because by default, on this installation of SQL, those are not equivalent unless I say to it, hey, I need you to compare this word to that word, but I need you to do it using the Latin 1 general case-insensitive, accent-insensitive collation, which is going to make it go, oh yeah, well, obviously now they're the same. So let's go back to our list of cities here, and now we're going to select cities ordered by name, and the default collation, Aachen, Aarhus, Berlin, Örebro, Zurich, which is, what makes sense to me as a British English speaker. But obviously, a lot of you didn't agree, because that's not the one you put your hands up for. What if we do the same thing, and we specify the Latin general collation? Well, we get the same thing, because that's the default. But if we do the Finnish and Swedish collation, it goes, oh yeah, well, in the Finnish and Swedish alphabet, the letter Ö comes after Z. So Aachen, Aarhus, Berlin, Zurich, and then Örebro is the 26th, 27th letter of the Swedish alphabet. If we do it using Danish and Norwegian collation, it goes, yeah, well, obviously Berlin is first, and then Zurich, and then Örebro, and then Aachen, and then Aarhus. And you're thinking, but why? Now, Aarhus, the city of Aarhus, used to be spelled Aarhus. And then in 1948, there was a thing called the Danish spelling reform. So until kind of just after World War II, Danish was spelt kind of like German. It used the German, kind of German variant on the Latin alphabet. And then for reasons I'm sure I don't need to explain, after World War II, a lot of countries are like, we don't want to be like Germany anymore. We want to be like Sweden, except not quite like Sweden. We're going to use a different And so there's 3 letters added to the Danish alphabet in 1948, and any places and people, you know, names of places, people, towns, those kinds of things, the convention was that you replaced AA with So Aarhus became Aarhus. And then in 2011, the citizens of Aarhus went, this is really affecting like our Google PageRank for tourism. Can we change it back? And they did. And so Aarhus became Aarhus, but it's still at the end of the alphabet, for the completely obvious reason that it's in Scandinavia. And so it goes at the end. Whereas Aachen is in Germany and is not in Scandinavia, so clearly that belongs at the beginning. Now, my exposure to this is I once saw someone on a Norwegian language version of Windows who had a text file called aardvark, and it was at the end of the file listing. And I was like, why is aardvark at the end? And they went, oh, that's Norwegian alphabetical order. And I'm like, but aardvark isn't a Norwegian word. And they're like, that's the problem. The computers cannot tell. There is not enough information in the word for SQL Server or Windows or anything to figure out what local conventions of orthography should be applied here. So if you do find yourself having to build a system that respects local conventions when it comes to alphabetical order, you can end up having to hack it and putting in another column. So you put in the column that you show the humans, and you put in another column that you use to sort things. I was on a website a couple of weeks ago where I was trying to pick my country in a drop-down list and I couldn't find it. And I realized eventually that the list had been sorted alphabetically in French and then translated into English. So Great Britain was at the point in the alphabet where Royaume-Uni would have been found. That took a little bit of head-scratching. So if you need to, you are going to need to put in enough clues that the computer can deliver the result that the human beings are expecting here. And sure enough, you get at what most people would consider in Denmark and Norway to be, yeah, it's alphabetical order, close enough. Now, when you come across these kinds of things, you know, like the little ASCII control codes and the weird alphabetical order conventions, they don't make any sense at first. If you're just sitting there, you know, you're on your computer and you do something, you get this weird result and you're like, why did it do that? And then you start digging into the history, and what you realize is that since we invented technology, really, smart people have been trying to solve real-world problems which are caused by people and culture and convention and politics and sociology and all these things that as, you know, geeks, we're like, oh, I don't care about that stuff, I just want to write code. But actually you can't write code without understanding the context behind it, because the technology we work with every day was informed by solving problems that were generated by these things. There is no such thing as politically agnostic technology. You can't even put words in alphabetical order without having to understand that World War II happened and that caused a bunch of stuff, and then some people voted on something and that caused a bunch of stuff. Now, let's take a look at our C, the little C sign here with a Sadir on it. Now, Unicode doesn't tell anybody how to do their jobs. What Unicode tries to do is to take everything that we were already doing and come up with a consistent way of encoding it. So Unicode says, all right, well, this character here, if you're French, this is just a letter of the alphabet that you have on your keyboard, so we'll give it its own code point. But if you're English, you are used to doing this as a letter C, and then you draw a little tail on it with a biro. So we'll give you a Unicode equivalent of taking a letter and drawing a little tail on it with a biro. We'll give you a thing called a combining character. Now, the brilliant thing about combining characters is you can stack them. You can take a Z, and you can go add one of those, and one of those, one of those, one of those, one of those. Now, on some devices, what you will get here is that your device will crash. This used to be a really good way to crash Android phones. On others, you get Zalgo text, which if any of you has ever looked up Tony the Pony on Stack Overflow, you'll have seen Zalgo text is what you get if you try and use regular expressions to parse HTML. Now, let's go back to our old friends Motley Crue. Now, the first time Motley Crue, this is the heavy metal umlaut. This is a thing that American rock bands do because they think it looks cool. And the first time Motley Crue toured in Germany, after the first show, they're like, why does everyone keep shouting Mötley Crüe, Mötley Crüe? And they had to have it explained to them that in Germany, that says Mötley Crüe. Now, we could write Motley Crue as that, or we could write it as that. These are both valid representations, but are they the same? And again, what Unicode does says, well, we're not going to decide for you. We are going to give you the tools that mean you are responsible for making the decision. So Unicode defines 4 different ways of normalizing a string. There is a thing called the NFD, which is the canonical decomposition. This means you take the string and you break it out into the maximum number of code points. If you've got a C with a little tail, you split it out into a C and a combining character. The canonical composition is the opposite. If you've got a C plus a tail, you can combine that into a single code point. And then the K stands for compatibility because C was already taken for canonical. This means, look at the characters, and they don't have to be exactly the same code point, but do they mean the same thing? And then there is a decomposed and a composed normalization form for compatible. Now, if we take a little chunk of code here in .NET, these are the way normalization forms are implemented in C#. And we're going to go through each one of those forms, and we're going to do a string comparison based on that normalization and see if the result we get is equivalent. So if we take these 2 characters here, we've got Motley Crue, and we've got Motley Crue using a combining diaresis, and we're going to run that code. And what we get out is, okay, they're not the same string. They are not binary equivalent. If we just say, does this equal that? It says, no, those are not equal. But they are considered equivalent under all 4 forms of normalization. So we can say these things are the same. Now, Unicode also supports fancy letters. We've got plain text here in circles, and we've got plain text not in circles. Are these the same string? Well, again, we're going to run this through our little comparison code here. And out of the box, it says, no, they are the same length. They are not equal. And they are not equal unless we impose the compatibility normalization form, at which point it's like, well, that P in the plain text in the circle, that's just a letter P. Come on, we're going to treat those things as the same for this purpose here. Now, my personal experience with Unicode and character encoding all goes back to one day at work about 6 years ago where I got into the office one morning and someone said to me, oh, dude, I think we've been hacked in the night. And I'm like, now, you get this all the time when you work in tech, right? Like, I've been hacked. No, you haven't been hacked. You've accidentally right-clicked and view sourced and put that away. You haven't broken Facebook. It's fine. No, your files are on your desktop. Look, they're behind that window there. You haven't been hacked. But sometimes, somebody who is a really, really competent security engineer comes up and goes, I think we've been hacked. And I said, why do you think we've been hacked? There's Chinese in the event logs. And I go and look in the event logs, and sure enough, there is Chinese in the event logs. Now, we are a company of predominantly English-speaking British people based in London, doing English language services for predominantly English and Western European customers. We don't have any Chinese programmers. We don't have any Chinese programs that we know about. We don't have any Chinese or no Chinese language support in any of our systems. We're like, where is this coming from? And so, we do the standard thing, right? You start looking through the firewall logs, see if there's any evidence of a breach or intrusion. You dig through the database, see if you can find Chinese in any of the tables. Is this an injection attack? You go and tell business people that we are investigating a potential data breach incident, and we'll have an update for them in 15 minutes, which means that me, as the boss, can get a cup of coffee and shitpost on Twitter. And that was the winning strategy, because I had the answer before any of them did, because I put this on Twitter, and immediately someone says, that looks like a Unicode mapping error. And Fake Unicode, which is a wonderful Twitter account that you should follow if you're into this stuff, says, yeah, the low bits are all null. This is probably UTF-16LE being mistaken for 16BE or vice versa. And I look at it and go, yeah. I should probably figure out what that means. So I dive headfirst into the teach yourself Unicode in 90 minutes rabbit hole. And this is what I learned. If you take the word delete on Microsoft Windows and JavaScript and Java and it's kind of most mainstream operating systems, they use 16 bits for each character by default because it's fast. Because memory is relatively cheap, and knowing the length of a string by just saying, well, if it's this many characters, it's going to be double that many bytes in length, makes a lot of memory management operations really, really fast. So under the hood, that fact, by the way, is like 95% true. There are edge cases, there are exceptions, but predominantly, internally, Windows, JavaScript, and Java use 16 bits for each character in a string. So the word delete looks like this. Now, if those get swapped around so that the big end becomes the little end and vice versa, what you get at the other side is Chinese. And if you put this on YouTube, you get helpful people telling you what the Chinese means. So that one is dismembering the body of some livestock. The next one is to climb. There's a category of textile and fabrics. And gems and pearls and jade formerly put into the mouth of a corpse. So I'm like, this is either a really freaky ransom note or it's a technical problem. So next question, this is clearly what's going on. Like you take the word delete and that's exactly the text we could see in the event logs. So this is SQL statements being accidentally flipped around. We're like, well, why is it getting flipped around? Turns out what happened is that we had a virtual network set up with a database, a couple of web servers, and one of the virtual network switches was about every 3 minutes it would drop 1 byte. And it wouldn't tell anyone it had done this. The byte would just go missing. And so everything would get shunted sideways by 1 byte without any indication it had happened. And the thing on the other end would be like, yeah, delete from starware. OK, Chinese now, that's fine. And yeah, so that's exactly what happened there. Now, this UTF-16 encoding, which most operating systems use internally, on desktop, laptops, local storage, it works brilliantly because it is fast. Once you get out onto the World Wide Web, the balance kind of shifts. Because on the web, bandwidth matters more than memory. We want to minimize the amount of data we are sending backwards and forwards. When we browse the web, we send email, we do all this kind of stuff. Now, if we take this web page, this is Privyet, which is hi, in Ukrainian this time, and we look at that in UTF-16. Now, all of the text on this page, the things that the humans are going to look at, is all in Ukrainian Cyrillic, but this is HTML, which is based on ASCII. And ASCII only uses the 7-bit, 127-character encoding. So these bits are the bits that need to be in Unicode. And the rest of it, we are sending all of these zeros that don't say anything. They don't need to be there. Now, they do need to be there, because if we take them out, we're going to get Chinese in the event logs. But 44% of this document in UTF-16 is just nulls. So HTML, even if the language of your documents is not based on ASCII, all of your markup, your tags, your quotes, your HTML attributes, all your CSS, hopefully your JavaScript. If anyone wants to write JavaScript in Ukrainian Cyrillic, it wouldn't be the dumbest thing anyone ever did in JavaScript, but it would be in the top 10. Most of that is still going to be ASCII. And so we needed an encoding system that didn't waste all this time on text encoding formats which are predominantly ASCII-based. And so UTF-8 was born. And UTF-8 is brilliant. The rule of UTF-8 says you see a byte that starts with a 0, that is 7-bit ASCII, same as it was in 1965. So all of the ASCII documents from before the moon landings, those are valid Unicode UTF-8 without changing anything. If you see a character that starts with a 1, this is a multi-byte encoding sequence. If you see 10, you are halfway through a letter. You need to backtrack a little bit. Okay, 110, that means this is the beginning of a 2-byte sequence. 1, 1, that's how many. 0 is the spacer. And then the red characters, that's where you actually read the numeric value. If you see a 1110, that's a 3-byte encoding sequence. If you see 11110, this is a 4-byte encoding sequence. Now, they kind of stop there, because the longest round-trip encoding we've got is into a thing called UTF-32, which is a 4-byte sequence. You could go higher. You know, we could have UTF-64, UTF-128. This thing scales up to an 8-byte encoding sequence. But this gives us a huge amount of headroom. It gives us space for all of the characters in all of the alphabets that human beings use or have ever used historically. It gives us a bunch of space, so when we make contact with benevolent space aliens, we can start sending email backwards and forwards to them, which I'm looking forward to very much. And it gives us space to invent new languages. And you're thinking, we don't invent new languages, do we? Well, we do. There's a new language that we invented within my lifetime that most of you have probably used today, which is the language called emoji. It's invented in Japan about 1999. It was an artist, Shigetaka Kurita, was working on a project for Docomo, the Japanese mobile phone, biggest Japanese mobile network. And they had a product called iMode, and they wanted something that made like weather forecasts and traffic reports look interesting. And so he created this, the original set of emoji, which is now in the Museum of Modern Art in New York. And within about 6 months, you couldn't sell a phone in Japan that didn't have emoji, because this just went, they absolutely loved it. So when Apple launched iPhone in Japan in 2008, it had to have emoji support, which meant people all over the world suddenly worked out, hey, if you go into iPhone and you set your keyboard language to be Japanese, you get all these cool little extra characters on there. So you could start sending your friends text messages, and they'd come back, how did you send the smiley face? How did you send the little grinning devil and stuff? Now, this prompted a lot of questions. Some people are like, well, why does emoji have support for like sushi, but it doesn't have tacos? Like, I like tacos. Where are tacos? And other people going, okay, pilot, doctor, engineer, these are all men. And they're all, this gets us into semantics. Are they white men or are they yellow men? Because neither of those is really a good answer. But certainly emoji was not very good at allowing people to express their own identity. So in 2015, Unicode took a huge step forward because they introduced the ability to modify the skin tone that was used on things like thumbs up. And they did it using combining characters. Just like we did for the Motley Crue umlaut, you got a thumbs up plus this, the medium dark skin tone would give you this. Now, every year, there's a fresh batch of emoji published and added to the Unicode specification. And they have this huge array of different, gender identities, family configurations, occupations, all these kinds of things. And the way that they do it, I think, is brilliant, because they use all of these mechanisms that they built into the design of the encoding system. So the Unicode for female astronaut is woman, then a thing called a zwidge, which is a zero-width joiner, and then rocket. And if you send this to someone, on an old Android phone, you get woman rocket next to each other. If you send this to someone on a modern Android or iPhone, you get female astronaut. And you can even add skin tone modifiers to it. So if you want the official emoji of Mae Jemison, who was a mission commander on the space shuttle, you send woman, you send dark skin tone, you send a zero-edge joiner, rocket, and you get that. Now, flags is where emoji really gets going, because the flag of Denmark is encoded using, there is a block of alphabet characters, the regional indicator symbol letters, A through Z. And Denmark has the ISO code DK, and so the flag of Denmark is the regional indicator D, regional indicator K. And all of the countries in ISO, that's how it's encoded. England is not a country, according to the International Standards Organization. Don't ask, it's complicated. But the flag of England is in emoji. Now, they introduced a set of characters to Unicode called alphabetic tags, which they put in about 1992, thinking this might be a good idea. And then no one used them for a long time, and then they took them out, and someone went, no, quick, put them back in. The flag of England is using them, because the flag of England is a black flag, followed by tag G, B, E, and G for Great Britain, England. The same is done for the flag of Scotland, the flag of Wales, and the flag of Texas, which is USTX, is in there as well. Those are currently the only 4. But there is this mechanism for putting in flags which are not countries recognized by the United Nations. And the pride flag is a white flag, a zero-width joiner, and a rainbow, which I think is rather nice. Now, does anyone know the name of this country? Does anyone know the official name of this country? Yeah. Which China? This is the flag of the Republic of China. Not to be confused with the People's Republic of China. The Republic of China is the country most people call Taiwan, but officially it is the Republic of China. And this flag on the mainland in the People's Republic of China is a symbol of support for Taiwanese independence, and they don't like that one bit. So if you go onto your iPhone in British English, which is what I have, and you can be like, hey, type in Taiwan, and pop, there it is, and you get the flag come up. But Apple obviously want to sell iPhones in China, because there are 3.5 billion people in China, and quite a lot of them will have money to buy iPhones. And so what Apple did is they said, all right, well, if you go into your regional settings and change it to China mainland, the flag disappears. And it's not there. The flag of Taiwan doesn't appear anymore, and it will never appear, because this is the deal that Apple did to be able to sell iPhones in China, is they said, we will take out the symbol that your government doesn't like because you think it's a symbol of support for Taiwanese independence. Now, this was Apple's solution to it. Microsoft went a step further. If you go onto my Twitter profile right now, it's got a little Danish flag, because I like the thing where you change your Twitter name to say where you are and what you're doing. And you can see that. Now, that is the DK indicator. But Twitter's web interface doesn't use the operating system to draw emoji. Twitter's web interface draws images, little PNGs, that are part of the website. Now, if you go in to edit my Twitter profile, on a Mac, you get the thing on the left, which is the Danish flag. On Windows, you just get DK. Because Windows has decided we are not touching the whole China-Taiwan thing with a barge pole. We're not going near it. There are no regional flags in Microsoft Windows, and there probably never will be. The only flags that are natively supported on the Windows operating system are the pride flag, the skull and crossbones, and the checkered flag for winning a Formula One race. So as far as Windows' mission statement on flags, gay pirates are winning, and everyone else can get in the bin. Which I can kind of get behind. Like, that obviously saves them a lot of complicated meetings. Now, I want to leave you today with something practical that you can take away and use. If you have a look at the logo type for my company, and we touched briefly on this earlier, the T and the I there, they're kind of stuck together. And this is that thing we talked about, which is a typographer's ligature. And it's still just TI. That's regular 7-bit ASCII under the hood. But this font, which is called Lato, will combine those two characters and turn them into this single glyph. And it turns out that we can use ligatures in programming as well. Anyone recognize this language? So it's a very nice solution to FizzBuzz. The language is F#, and what the actual text in the file is this. But this, same code, same editor, different font. And the font is a thing called Firacode. And Firacode is a programming font that uses ligatures and gives you things like, if you have the equals, equals, equals in JavaScript, it gives you an equal sign with 3 bars on it. It gives you little arrow operators. It gives you, function maps and closing brackets, all kinds of things. And I really, really like Firacode. There's a couple of others. This was the first one. There's now about 10 or 15 of these floating around. And I think they're brilliant. I think they improve the readability of code. They make screenshots look good. You know, there's a certain yay, I work in the matrix going on here as well. So yeah, if you want to get the wonderful power of ligatures in your code editors that you work with every day, go check out Firacode, download that. It's a font, so it works with pretty much everything. Any editor, Visual Studio, VS Code, Eclipse, they all work with it, and you can get code that looks like this. Now, last thing that I want to share with you today is I mentioned at the beginning that a lot of the stuff in this talk is kind of not necessarily stuff that I learned traveling, but it's stuff where I was traveling and I went, that's weird, why do they do that way? And I went and started digging with it. And the first time I went to Ukraine, which was in 2016, I was walking around the place. I didn't read any Cyrillic. I started learning the language, the alphabet after I got back. So I'm wandering around the place. I can't read anything. I can't read the restaurant menus. I can't read the road signs. But I can read the license plates on the cars. I thought, that's weird, you know. And so I started digging into it. And I discovered that there's a thing, 1965 actually, the same year as ASCII was proposed, there was a thing called the Vienna Convention on Road Traffic, which all the countries in Europe, they signed up to this thing, yeah, we will agree to play by these rules so that we can drive cars into each other's countries and stuff. And one of the stipulations of the Vienna Convention is that your license plate could only use the Latin alphabet, like the vanilla ASCII English alphabet. Now, license plates in the Soviet Union in 1965 looked like this. And I'm guessing that there was a meeting somewhere where, because the Soviet Union signed the Vienna Convention. They're like, yep, we're fine. And I'm guessing at some point someone said, but what if you need to take your car out of the Soviet Union? And they went, comrade, you cannot drive car out of Soviet Union. But if you did, when you got to the border, if you had all your travel papers to be able to leave, they'd give you temporary license plates. And presumably, if the license plates didn't come back, your family went to the gulag, so you would bring your car back there. But then when the Soviet Union, kind of collapsed in the 1990s, all of the former Soviet republics, Ukraine, Russia, Belarus, they all overhauled their vehicle registration system. And so now their license plates look like this. And what they did is they took the Russian or the Cyrillic and the English alphabet, and they looked at the set of, not the set of letters, but the set of glyphs, the shapes that exist in both of those alphabets. And that is the subset that are used on vehicle registration plates in, this exact subset is in Ukraine. Russia is almost the same, Belarus is almost the same. But this is the set of letters you'll see on Ukrainian license plates. And if you rearrange those, you get the word Pike Matchbox. So next time somebody says to you, hey, I'm going to send you a file in plain text, just say to them, do you know Pike Matchbox? And if they say, yep, then you're good. They know about big endian, little endian, UTF-8, UTF-16, the history of ASCII, cohuept character encoding, Cyrillic code pages. And if they say, no, what's Pike Matchbox? Then they can send you plain text, and whether you can open it or not is anybody's guess. Thank you, NDC.